Have you ever stopped to think about why you instinctively reach for a dark, heavy sweater in the winter, but a light colored t-shirt in the summer? Well, the secret is this invisible, powerful force that's, all around us all the time. Heat. It's what's cooking your dinner, it's why you chose that outfit, and it even drives the weather. So today, we're going to pull back the curtain and really get into the science of it all. All right, here's our game plan. First up, we're going to see why you can't always trust your own hands. Then, we'll dive into the nitty-gritty. What's the real difference between heat and temperature? After that, we'll look at how we actually measure it, how it gets from point A to point B, and finally, we'll solve that clothing mystery once and for all. Okay, so first things first. How do you tell if something's hot or cold? You touch it, right? I mean, we all do. But what if I told you that your sense of touch, well, it's a bit of a trickster. Turns out what we're feeling isn't always the full story. So let's put this to the test. There's a classic experiment that really shows how weird our perception of temperature can be. And honestly, you can do this yourself right now with just 3 bowls of water. It's the perfect way to see why we need something a little more reliable than just, well, us. Okay, so check this out. The hand that was in the cold water, it thinks the room temperature water is warm. But the hand that was in the hot water, it feels that exact same water as cold. So which is it? Your brain is getting 2 totally different signals from the same source. And that is precisely why we can't just rely on our sense of touch to measure temperature. So since our hands are, let's face it, pretty unreliable witnesses, we've got to get a little more scientific. This brings us to 2 words that we all use but often get mixed up: heat and temperature. They're related for sure, but they are not the same thing. Let's clear this up. First up, let's talk about heat. The best way to think about heat is as energy in motion. It's the actual flow, the transfer of energy from one thing to another that gives us that sensation of warmth. And here's the key. It always flows from a hotter object to a colder one. No exceptions. It's a basic law of the universe, kind of like gravity. Okay, so if heat is the energy that's moving, what's temperature? Well, temperature is the measurement. It's the scoreboard. It's that reliable number that tells us exactly how much of that heat energy an object actually has. It's the objective fact, no matter what our confused hands are trying to tell us. This really lays it all out, doesn't it? Heat is the cause, temperature is the effect. You add heat to something, its temperature rises. You take heat away, its temperature drops. It's a direct relationship. You can't really stick a probe in and measure heat flow directly, but you can absolutely measure its result, which is the temperature. Okay, so we know what temperature is, and we know we can't trust our hands. So how do we actually measure it accurately? Well, for that, we need the right tool. And that tool, of course, is the thermometer. It's a simple idea, really. It just uses some kind of material that expands or contracts in a really predictable, consistent way as the temperature changes. That way, we get a reliable number every single time. Let's take a look inside a classic clinical thermometer. Now, this thing is actually a pretty clever piece of design. It uses mercury because that liquid metal expands and contracts super consistently with temperature changes. The range is pretty small, right? That's because it's calibrated just for the human body. But the coolest part is that little kink or bend near the bottom. That's the real genius move. It acts like a one-way valve, stopping the mercury from falling back down immediately, which gives you enough time to actually read it accurately. So, we've established that heat is energy in motion. It never just stays put. It's always moving from warmer places to cooler places, trying to even things out. And it turns out it has 3 main ways of making that journey. And here they are: conduction, convection, and radiation. Those are the 3 big methods of heat transfer. Let's break down each one. First up is conduction. This is heat transfer by direct contact. Think of it like a row of dominoes. One particle gets hot, starts vibrating like crazy, and bumps into its neighbor, which starts vibrating and bumps into its neighbor, and so on down the line. That's why if you put a metal spoon in hot tea, the handle gets hot pretty fast. Metal is a great conductor. On the flip side, the plastic handle on your frying pan stays cool because plastic is an insulator. It's terrible at passing that energy along. Next, we've got convection. This one happens in fluids, so liquids and gases. It's all about movement. When you heat up a fluid, it gets lighter, less dense, and it starts to rise. Then the cooler, heavier fluid sinks down to take its place, gets heated up, and it rises too. This creates this constant circular motion, a current, that carries the heat with it. And this happens on a huge scale in the real world. Ever heard of sea breezes and land breezes? That's pure convection. During the day, the land heats up faster than the water. The hot air over the land rises, and the cooler air from over the sea rushes in to fill the gap. That's a sea breeze. At night, it reverses. The land cools down faster, so the cool air flows out towards the sea. It's one giant planetary convection current. And finally, we have radiation. Now, this one's the real standout because it doesn't need any stuff to travel through. It moves as electromagnetic waves, just like light. This is how the sun's warmth travels millions of miles through the empty vacuum of space to reach us. It's also the heat you feel radiating from a bonfire, even when you're not touching it. It's pure energy on the move. And you want to talk about speed? Radiation is the absolute champion of heat transfer. Because it travels at the speed of light, there is simply no faster way to get heat energy from one place to another. All right, so let's bring this all back to where we started, that whole clothing mystery. Now that we understand how heat travels, we can finally figure out why we dress the way we do. It really comes down to how different colors deal with radiation. Think of light colors as being like a mirror for heat. They reflect most of the sun's radiation away from you, which helps keep you cool. Dark colors, on the other hand, are like a sponge. They absorb that radiation, converting it to heat and making you feel warmer. That's it. That's why it's white t-shirts for summer and dark coats for winter. And what about that cozy woolen sweater for winter? Well, here's the secret. The magic isn't just in the wool itself. It's in the air that the wool fibers trap. Air is a fantastic insulator. So that sweater creates a buffer of trapped air around your body, which stops your own body heat from escaping into the cold. It's your personal wearable insulation. So there you go. From the breeze at the beach to the reason you wear a certain jacket, the science of heat is everywhere, working behind the scenes. It's way more than just feeling hot or cold. It's about the basic rules that govern how energy moves through our universe. So next time you feel the warmth of the sun or hold a hot cup of coffee, just think about what's really going on. Now that you know the rules, what else in your world does this explain?